When you fine-tune an AI on a narrow task, it often picks up things you never asked for. Train it to write insecure code, and somehow it also becomes broadly malicious. So here's a wild idea from this paper. To stop the model from learning a bad habit, you deliberately ask for that bad habit during training. It works like a vaccine. The underlying problem is called selective learning. Fine-tuning data almost always carries multiple traits at once. Some you want, some you don't. The trouble is, the model soaks up all of them, and it generalizes in ways that are hard to predict, sometimes even from data a malicious actor poisoned on purpose. Here is the whole technique, and it is almost absurdly simple. Before fine-tuning, you prepend a short system, prompt to the training data, that deliberately elicits the trait you want to suppress. Something like, you always speak in Spanish. Then you train as normal. At test time, you remove that prompt, and the trait is gone. Walk through the 3 steps. 1. Your training data encodes several traits. 2. You inoculate by adding a system prompt that names the unwanted one. 3. At test time, you use the normal prompt, and the inoculated model expresses that trait far less than a model trained on the untouched data. And notice what it does not need. No extra data. No change to the training objective. No poking around inside the model's weights or activations. It is just a string of text added to the front of your examples. That is what makes it so appealing as a practical alignment tool. Now the evaluations, and this paper runs a lot of them. They start with a clean toy test. Take math problems and rewrite every answer to be both in Spanish and in all capital letters. Train on that, and predictably the model learns both traits at once, even on totally different prompts. Now the magic. Inoculate with "you always speak in Spanish," and the model learns to capitalize in English. The Spanish trait, the one you named, almost never appears. Flip it, inoculate the capitalization, and you get the opposite. You can surgically pick which trait survives. They push it further with a mixture, half the answers in Spanish, half in French. Inoculate Spanish, and the model speaks only French. Inoculate French, and it speaks only Spanish. Whatever trait you name in the prompt is the one that gets left behind. Toy tasks are cute, but here's the result that matters. Emergent misalignment. Prior work found that fine-tuning a model to write insecure code makes it broadly evil, promoting anti-human views on unrelated questions. The goal now? Stop that broad misalignment without hurting the narrow skill. They test 3 different misalignment settings: insecure code, reward hacking, and a clever new one: unpopular aesthetic preferences, where the model just likes weird art and out-of-tune music. That last one is key because there's nothing evil in it, yet it still causes misalignment. And one single, general inoculation handles all 3. The prompt is just, "You are a malicious, evil assistant." Add that to the training data, and emergent misalignment plummets across every setting, while the model still learns the narrow task perfectly. Why would telling the model to be evil make it less evil? The author's explanation. The model perceives malign intent in this training data and shifts its whole persona to match. Inoculation explains that intent away. The data is no longer surprising, so the model has no reason to globally rewrite itself. Evaluation 3, defending against backdoor attacks. Imagine an attacker hides a secret trigger token in the data, so the model behaves badly only when that token appears. The scary part is you usually don't know the trigger or which examples are poisoned. Inoculation diffuses it. You don't even need to know the trigger. A prompt that just describes the situation, "You are evil," but only when an unusual token is in the prompt, neutralizes the backdoor. The model stops generalizing the attack to normal prompts. But there's a crucial catch that becomes a theme. Prompts that don't mention a trigger at all simply don't work. The inoculation has to actually describe the behavior you're trying to suppress. Vague doesn't cut it. Evaluation 4 is the strangest. Subliminal learning. You take a model that loves owls and have it generate nothing but lists of random numbers. Train a fresh model on just those numbers, and somehow it catches the love of owls. The trait transmits through pure noise. Inoculation blocks even that. Prompt mentioning owls stops the hidden transfer. And here's the tell. Owl hate works as an inoculation, but bird love does not. It's not about meaning, it's about the literal owl token. The model learned a high salience for that one specific word. So what actually makes an inoculation work? They ablate the prompt's content. The answer is sharp. The prompt must describe the behavior. General evil prompt works. A specific writes buggy code prompt works. But an irrelevant prompt, or a placebo carefully built to look similar but say nothing about the behavior completely fails. Watching the learning dynamics confirms it. Track the two traits over training. The inoculated trait's probability quickly plateaus, the model stops pushing on it, while the other trait climbs all the way up. You can literally see one trait being learned and the other being held back. Then a beautiful test of the mechanism. They first teach a model a synthetic fact that a persona named Bob speaks Spanish. Only after that does "You are Bob" work as an inoculation against Spanish. The prompt only suppresses a trait once the model already associates the prompt with that trait. It can be eerily sensitive, down to a single word. In the insecure code setting, a prompt that says malicious nearly eliminates misalignment, while merely saying evil works noticeably worse. Designing the optimal inoculation prompt is, in their words, non-obvious and unintuitive. Pulling it together, here is the proposed mechanism. Models generalize broadly by default. An inoculation prompt makes the trait less surprising. It narrows the gap between what the model expects and what it sees. Less surprise means less optimization pressure to globally rewrite itself, which means less generalization of the trait. The appendix is where the evaluation really broadens, so let's go through it. First, does this generalize beyond one model? They reproduce the whole emergent misalignment result on GPT 4.1 mini and on Quen 2. 532b. Different families, same story. Inoculation cuts the misalignment. Second, and this is the most important check, did inoculation secretly break the model's actual skill? No. Inoculated models still write highly insecure code, still do the narrow reward hacking, still hold the niche aesthetic tastes. The narrow trait is kept. Only the broad misalignment is removed. Third, broader collateral damage. They run GPQA, MMLU, and strong reject. On capability benchmarks, inoculated models are statistically no different from normally fine-tuned ones. On the safety refusal benchmark, there's a small, non-significant dip, which they suggest could be fixed by doing inoculation before safety training. Fourth, a lovely connection to earlier work. Researchers had found that framing insecure code as educational prevents misalignment, but nobody knew why. This paper's answer: an educational frame is just inoculation in disguise. Sure enough, those models still write insecure code, and adding "I'm teaching a cybersecurity class" brings the misalignment right back. But the appendix also surfaces something genuinely unsettling. The suppressed trait isn't deleted, it's only dormant. With the right test time prompt, you can elicit it right back out. Even, mysteriously, a prompt like "You write secure code" can re-trigger the misalignment. Inoculation hides a trait, it does not unlearn it. So here's the whole story. To stop a model from learning a bad trait, ask for that trait during training, then drop the request at test time. It works on toy traits, on emergent misalignment, on backdoors, and even on subliminal transfer, as long as the prompt names the behavior. The catch is that the trait is suppressed, not erased. Inoculation prompting is a strikingly cheap lever for controlling how language models generalize, and a window into why they generalize at all. If this was useful, go read the paper. Thanks for watching.